The work presented is titled Structuring Cyber-Physical Systems for Distributed Control with IEC 61499 standard. Smart factories in Industry 4.0, bridging the gap between automation and personalization, are made up of many components that must be increasingly autonomous and operate in parallel. Increased parallelism improves performance while complicating system development due to a greater number of interactions between components. This complex interaction makes it necessary to use software engineering techniques such as cyber-physical systems (CPEs). However, the need for a distributed architecture and the requirement for flexibility has revealed a gap in modularity standards for the industry. In this sense, the implementation of CPEs requires the use of controllers that can be communicated through standardized protocols, which nowadays reflects a challenging task. Therefore, the objective is to define an approach to integrate systems with software, cyber, and hardware, physical, in the design of distributed automation based on the IEC 61499 standard. Basing on CPE's basic structure and the IEC 61499 standard models, the manufacturing system automation architecture is modeled as a collection of devices divided into resources, interconnected and interacting with each other through one or more communication networks, which could be represented as a cyber-physical system constitution through IEC 61499 standard. To validate the proposed approach, the following methodology has been considered. We take a package classification system by destination as a study case. This system has three double-axing pneumatic actuators and various position sensors. Schneider Electric's Next Studio development platform has been selected. In Next Studio, the model view control pattern allows integration with a simulation model. Control logic for each actuator is obtained by creating FBs that interact as control software units, containing algorithm and execution control chart with inputs and outputs of data and events. Finally, the deployment is carried out on 4 soft PLC devices running for Next Studio runtimes on one PC. One for the HMI of the system model, which represents the real process, and 3 for the Next Control DCS mini PLCs. The Ethernet segment models the communication channel for all devices instances. Thus, each pneumatic actuator in the system is controlled by an individual PLC and identifiable by its unique port ID. Finally, conclusions are presented. The close relationship between CPS and IEC 61499 standard enables a distributed way to design control applications in industrial automation in which each control, communication, and physical process are covered in a graphical modeling language. The proposed CPS approach is better suited to intelligent manufacturing requirements such as modularity, reusability, and adaptability, since there is the possibility of generating new, even more specialized components from those already created by reusing their software functionalities by simply extending or adapting FBs with minimal modifications.